So hello everyone, welcome to the third lecture of the mini school about two-dimensional categories. So we will start this lecture by recapping what we did last week, just briefly, also because we have had some issues with the video, so just to be sure. Last week we spoke about two categories, so we introduced the notion of two category. We said that a two category has objects, morphisms, but also morphisms between morphisms that we call two cells. So like this alpha between F and F prime. We still have identity morphisms, the usual ones that we have in a one-dimensional category, but we also have identity two cells like this one. So identity of a morphism F. And since we have two cells, we need a way to compose two cells. And actually, we have two different ways of composing two cells. We can compose them vertically, so we attach the two cells vertically, or we can compose them horizontally, so we put them next to each other. So the vertical composition will be between two cells with same source, with same object. Between two cells, between arrows with the same source and target, while horizontal composition is between two cells that share this medium object, B in this case. So we saw that there are different axioms that the two category needs to satisfy, and one important is that if we have a picture like this with four different two cells, we can either compose alpha and beta horizontally and gamma and delta horizontally, and then do the vertical composition of the two composites. Or we can also compose alpha and gamma vertically and beta and delta vertically, and then compose horizontally. And the result we get is the same. So we have this interchange law. Then we saw how to work with pasting diagrams. So how do we understand these kind of diagrams? And we saw some examples of categories. So the first one is CAT, the two category of categories, functors and natural transformations. That's kind of the archetypal example. Then we said that there are two categories of functors as well, and so we can construct two categories of stacks that generalize sheaves to one-dimensional. And then we spoke about two functors that are the natural arrows between two categories, and they preserve all these all the possible compositions and identities that we have. And we also have two natural transformations that are just like natural transformations, but now we have also a compatibility with two cells. And then we ended the second lecture talking a little bit about bicategories. So they are a weak version of two categories. And this means that we don't ask anymore that composition of arrows is associative, but it's only weakly associative. This means that if we do G, F and then compose with H, or if we do F and then H compose with G, these two are not the same, but they are only isomorphic. So some people work with this kind of weak two-dimensional categories, the bicategories, but every bicategory is equivalent to a two-category, so to a strict two-category. And an example of bicategory is that of spans in a category C that we saw, and that's where we stopped last lecture. I just wanted to add one more thing to this picture of two categories and bicategories before we move on, and this is about pseudo-functors. pseudo-functors. So what are pseudo-functors? They are a weak version of two functors. So they are so we are talking a little bit about, oh, it's working really badly today. What's happening? No, I don't know why this is not working. Not working properly. Because I write and it doesn't write. How should I solve this problem? Let me do like this. And maybe this precise thing I can also not write it. So what is a pseudo-functor? It is a functor between bicategories that preserves identities and composites only up to isomorphism. So it's not true anymore that f of f composed with g is equal to f composed with f of f composed with f of g, but it's only true up to isomorphism. And the same for identities. So identity is now preserved only up to isomorphism and not on the nose. All right, so that's everything I wanted to say about bicategories, because today we are going to speak about double categories. So hopefully this will now work. Otherwise I can try and change maybe browser. Yeah, because this is not working properly. Doesn't really react. Okay, let me stop the sharing of the screen. So I will try to change browser. Okay, I will also do that. I will try with a new notebook, but also with a different browser, because I think last time I used a different browser and it was working better. Let me just sign in with a different browser. While I sign in, I remind you that we are now talking about double categories, and we said in the first lecture that double categories are categories internal to the category of categories, and we'll see what this means in a minute. And we'll also see why these are different from two categories. I'm signing in. Okay. I will start a new notebook, so. Okay, now I share my screen again. And hopefully. Yes, the recording will be on the YouTube channel of NITheCS. Unfortunately, the one from last week will not be there because there has been some issues with the recording, but all the other ones are going to be there. Okay, I hope this will work now. I really, really hope so. Okay, so we are talking about double categories. It's not working super well, but better than the other ones. Okay, so what is a double category D? It has a set of objects, just like a normal categories. Categories, so like A, B, C, and so on, D. Then it has arrows between objects. So from an object A to an object B, an arrow F. But then it has another kind of morphisms that we call pro-arrows. Pro-arrows. And we usually write with this notation, like a bar in the arrow. Say U, a pro-arrow from A to B. And there are different conventions about this. So what I usually do is I write arrows horizontally and I write pro-arrows vertically. That's what I do. But there are also people who do it the other way around. So they write pro-arrows vertically and horizontally and arrows vertically. So it's a matter of convention. And sometimes they are also called horizontal arrows and vertical arrows, but this seems very confusing to me because we don't all agree on which ones are horizontal and vertical. So I'm just sticking to arrows and pro-arrows. So we have two different kinds of, say, one-dimensional morphisms, arrows and pro-arrows. And then we have what is called cells or double cells. So if we have a square where the horizontal arrows are just arrows F and G, and now we have also two pro-arrows U and V. A double cell is something inside the square, so we call it alpha. So the idea is that the double cell will have an horizontal domain, in this case F, an horizontal codomain G, a vertical domain U, and a vertical codomain V. So these are ways of filling these kind of squares in the double category. Okay, and now we need to be able to compose all these kinds of things. So of course we will be able to compose arrows in the usual sense, but we will also be able to pro arrows in the other direction. And we will also be able to compose double cells. And now we can compose double cells in two ways. We can compose them vertically or horizontally. So if we have our double cell alpha, I will just not write all the objects, right? Just a double cell like this, alpha. And now if we have another double cell that has the same, that has as vertical domain, the vertical codomain of alpha, let's call it beta, we can attach them horizontally in this way, and we have a composite, horizontal composite. We usually write it just like this to say that we are attaching them horizontally. But also we can attach two cells vertically. So if we have that the first double cell as horizontal codomain, the horizontal domain of the second one, we can attach them vertically, and we can write like this to say that we are attaching them vertically now. And now we have these two different ways to compose double cells, but we also in this case, like in the case of two categories, we have some interchange laws. So if now we have four double cells, imagine we have four double cells like this. So we can represent double cells also in this more schematic way. Alpha, beta, gamma, and delta. And we want to understand what is this big double cell. Then we have two different ways. We can either first compose horizontally alpha and beta and gamma and delta, and then compose vertically. Or we can compose first alpha and gamma and beta and delta vertically, and then compose horizontally. And this gives the same result. So we have an interchange law. For double cells this time. And of course, we still have our identities. So every object now has an horizontal identity and a vertical identity. So if we have an object A in D, we can get identity of A the horizontal version. Okay, it's horizontal just in my notation, but the arrow identity, let's call it arrow identity. But we can also have the pro arrow identity. Pro arrow identity. And in the same way, we also have identity double cells. So they can be either between identity double cells of an arrow or of a pro arrow. So we have these two kinds of things. And all these objects need to satisfy axioms, of course. And these axioms are about associativity of composition, of any kind of compositions. And then we have unit laws. So we have the usual axioms that we require. Some sense? Okay, so this is what a double category is, and so on, say, but we were saying that this is an internal category in the category of categories, so we want to specify a little bit more what this means. So we want to see double categories as internal categories in CAT, and to do so, I will briefly tell you what is an internal category. So internal category in a category C. Okay, you have to think about this as a category that lives inside your category C. So what are the ingredients that we need to have a category? So we need a set of objects normally, but now this set of objects is going to be an object of the category. Let's call it C0. C0 is an object of C, and we think of it as the object of objects in the category. And now we need the objects, but we also need arrows. So we will also have an object of arrows. So we have another object of C that is the object of arrows. So elements of C or C itself, C1, sorry, itself represents arrows. So C0, it's called object of objects. And C1 is called object of arrows. And if you think about it, when we have an arrow, we need to be able to say what is the source or domain of this arrow and what is the target or codomain of this arrow. So the idea is that in ER, we will have two morphisms in C. One is source and one is target. And these morphisms associate to every arrow in C1 its source and target, and these things are objects in C0. Okay, so this is the idea. And moreover, to have a category, we also need a way to associate to every object the identity arrow on itself. And so we have this arrow from C0 to C1 that is the identity arrow. It selects identities among the arrows in C1. That's the idea. And all these arrows S, identity, and T are arrows in C now. And what's missing to have a category is also composition. And the way to encode composition is as an arrow. So I have these two arrows, source and target, from C0 to C1. So I can now compute the pullback of source and target. And it is this pullback I'm writing here. And now maybe I should write the diagram. So I have C1. I can go to C0 with source or target. Now I compute this pullback, right? Okay, this is the pullback. And now I can consider one of the two projections, and this gives me the composition of my internal category, comp. So I have a way to encode internally in the category C all the data I need for a category. So I have objects, arrows, identities, and composition. And then I can ask that these data satisfy all the usual axioms for categories, and these axioms now become a commutative diagram in the category C. So we're not going to see it in details, but we have these axioms of category that are written as commutative diagrams in C. Good. But now we want to see what this looks like when we do it in cat. So now our category C will be cat, the category of categories. And we'll see that we should recover double categories. So now we look at categories internal to cat. Okay, now so we have a similar diagram, similar to the one we saw here, but now this diagram lives in cat. So our C0 is now a category. So we have a category of objects, but we also have a category of morphisms, and we still have source, target, and identity. But now ST and identity are morphisms in cat, so they are functors, right? So what is this telling us? So C0 is now a category. So C0 in our double category is the category of objects and arrows. And C1 is also a category. C1 is the category of pro arrows and double cells. So what we are saying is that objects and arrows form a category, and pro arrows and double cells form a category. And we can put these two categories together in a coherent way to get a double category. So we will still have our composition, and now our composition is telling us how to compose arrows in C1. So this means that it's telling us how to compose double cells, right? And we can encode all the axioms of double category in this way. So they are precisely the internal category axioms in cat. Right. But now, in a similar way as we saw with the bicategories, with respect to two categories, we can also weaken this notion of double category a little bit to get what is called a pseudo-double category. So a pseudo-double category is for a double category what a bicategory is for a two category. So it's a weakened version that is useful because sometimes in applications you don't have a strict double category, but you still have this pseudo-double category. And these are weakly internal categories into cat. But what it means essentially is that pro arrows composition is weak. So it's not associative, for example, it's only weakly associative. So the idea is that on the arrow level, we still have an honest category, but now on the pro arrow part, on the C1 part, something is weaker. All right. But now you might wonder, how are these double categories useful? What are examples of double categories? And so we should see some interesting examples of double categories. So as you have seen, the idea of double category is that you have two different kinds of morphisms, arrows and pro arrows, and they interact with each other. So double categories are useful every time you want to consider two different kinds of morphisms between the same objects and see how these two kinds interact with each other. So let us see one first example. So our first example is the double category called rel. So it's the double category of sets and relations. So now our objects are sets. Our arrows are functions between sets. So this means that rel 0, so the 0 part, the object part, is precisely set, the category of sets and functions. But now we can add one more kind of morphism. Right, this is just a relation. So we represent it like this in our pro arrow notation. Is going to be a pro arrow from the set A to the set B, right? Just a relation. And now, what is a double cell in this double category? So we now have this situation. We have function f from A to B. Then we have another function g from C to D. And then we have a relation R in A cross C and the relation S in B cross D. What is a double cell alpha in ER? Alpha means that F cross G of R is contained in S. So we can only have one double cell inside the square. We cannot have multiples. So it's kind of what happens for posets in categories, that we can only have an arrow between two objects in a poset. It's either there or there are no arrows. And these arrows, this double cell means this property. So it means that if we take little a, little c in A cross C, so little a, little c is in R, this implies that f of little a, g of little c is in S. This is the property that we want. This is the double cell alpha. All right, and then we have a way to compose pro arrows, all the compositions that we want between double cells, and everything works well. So the fact that rel is a double category is saying that we can consider functions and relations together in a compatible way, and they talk to each other. So we can study sets with functions and relations at the same time. And now we can see a similar example, kind of a categorified version of this example, and this is called prof. So now we take categories and profunctors. So our objects are categories. Our arrows are functors. So again, prof 0, the 0 part is cat. But now our pro arrows are profunctors. And our double cells are just natural transformations between the right functors, profunctors, natural transformations. So this is a similar idea to that of sets and relations, but it is for categories. Right. Then we can maybe see another couple of examples. So we have a more algebraic examples that is called mod. So again, the idea is to see two different kinds of arrows between the same objects. So mod is the double category of rings and bimodules. Is the cat an object of cat? So you mean, is the category of categories an object of cat? That's the question. Technically, no, because cat is usually the category of small categories. And cat is not a small category. But if you enlarge your universe enough, you can construct a category of categories such that cat is an object of that category of categories. So it's just an issue of size. I don't know if this makes sense, but that's, you usually write a big cat, meaning that you are not restricting to small categories. Yeah. Okay, but of course, if you consider cat as an object of cat, then you are not considering its the two-dimensional structure of cat. You are just considering categories and and functors and not natural transformations. Okay. So I was talking about rings and bimodules. So this is a more algebraic examples. So what are the objects of these double categories? They are unitary rings. what are arrows? They are just ring homomorphisms. And what are pro-arrows? They are called bimodules. So again, our zero part, mod 0, is essentially the category of rings. But now we are adding a new kind of morphisms between rings that is called bimodule. So if we have two rings, R and T, a bimodule M is a trilinear map from R cross M cross T into M. Trilinear, right? And what are double cells? In this double category. So we have 4 rings, R, S, T, and Q. We have ring homomorphisms, F and G. We have these bimodules, M and N. What is a double cell alpha in ER is what is called an FG equivariant group homomorphism. So this means that if I do, so it's alpha from M into N, just a group homomorphism that satisfies this condition. So I can now do alpha of R, M, T. So this is an element of M because of the bimodule that I have, the trilinear homomorphism that I have here over M. So I can compute alpha of it. And I need to have that this is equal to F of R times alpha of M times G of T. That's it. So this is the condition. It's not really important, but the idea is that we have a new kind of arrows between rings that are called bimodules and are important in algebra, and then we have these double cells. So we can use double categories every time we have two kinds of arrows and we want them to talk to each other. But we also have that two categories are particular double categories. So we have two categories as double categories. And there are 3 different ways of seeing a two category as a double category. So the first one is, we can consider, so we have L a two category. Okay, so we can see L as a double category that is only horizontal in some sense, meaning that we can take all our pro arrows to be identities. So we have, the first way is all pro arrows are identities. Right, so we will have some objects, we will have arrows, but as pro arrows, we only have identities. right? And so what is a double cell here? It is just a two cell. So this is F, this is G. It's just a two cell in our two category. So that's the first way. Second way, we can do the same, but horizontally. So all arrows are identities. So now what we have is we still have objects, but now between the arrows are all just identities. But we do have pro arrows, and our pro arrows are just the arrows in the category. I'm just writing like this because now it is a pro arrows, but it's still just an arrow in the category. So like this. And our double cells are still two cells, but now they move from left to right, essentially. So this is the second way. And then we have a third way that's perhaps a little bit more interesting, that is called squares or quintets. And how this works is I have as objects the objects of L. I have as arrows and as pro arrows. I have arrows morphisms in L. So pro arrows and arrows are the same. Now our double cells are two cells seen in this way. So we now have squares like this, because both our arrows and our pro arrows are just morphisms in L. So we have squares like this, and we say that the double cell here is just a two cell between F composite with H and G composite with K. So our double cells are just two cells, all seen in the same way, in this way. All right, so we have these three different ways of seeing a two category as a double category. And I think we should stop here for today. And sorry for the delay. And thank you very much for listening. If you have questions, I'm happy to answer. Yes, the recording should be on YouTube of this session because it's recording, so yes. Okay, so if there are no questions, then thank you very much for coming, and I'll see you next week for the last session. And it's going to be on Tuesday instead of Wednesday, because Wednesday is holiday. Thank you. Goodbye.